Alright, so we're going to do 9-6C today. Cardioids we're going to talk about, and lemniscates. Okay, you do need to know the names of these graphs and how to spell them. So make sure you know how to name them and spell them, okay? There's 4 words. They're not very hard. Just make sure you can do that, because I'm going to ask you for the names of them, okay? And I don't want anyone writing like lemon biscuits on the quest. Like, I feel like that's a fair request, all right? So, okay. I don't know if you can figure out what a cardioid might look like, but it's heart-shaped, all right? So these graphs are heart-shaped, and this is the standard form for their equation. We'll just go right into that. It looks like R equals A plus or minus A cosine theta, or R equals A plus or minus A sine of theta. What do you notice about these compared to limesons? They have the same coefficient, right? So with a limeson, A can equal B. That's how you can name it a limeson. That's how you know that graph will look like more like a lima bean. And this graph will be a cardioid because it has the same coefficient. So that's how you can tell the difference, okay? We're just going to go into an example. And this is really just like what we did yesterday. It's the same steps. The graphs just look slightly different. Okay, so remember that the first step, step 1, was to decide whether it went through the pole, right? So decide if graph goes, actually, let's say decide where the graph goes through the pole, because, let's think about this for a second. Where the graph goes through the pole. Why will this graph always go through the pole? You can do it. I know you can do it. They have the same coefficient, so what's going to happen when I solve? It's going to be equal to 1 or negative 1. Aren't cosine and sine both on the unit circle with 1 and negative 1? Okay, so we're always going to get an answer there. Okay, so it's not the same as a limeson where maybe it doesn't. It will. Okay, so let's go ahead and set that equal to 0 and do the step. Okay, so subtract over the 4, divide by that positive 4, and you're going to get negative 1 equals the sine of theta. Okay, so now where does sine equal negative 1? Thank you, 3 pi over 2. So I did say I was going to do degrees, didn't I? Let's do that. Let's just flip-flop it to degrees. So 270 degrees. Okay. Now, notice that we are skipping the step of, is it a flattened loop? Does it have 2 loops? That's not the case here. Okay, so you don't have to do that step like you did with the limeson. But you do have to decide where it goes through the pole, and then step 2, you're going to evaluate either sine or cosine at negative 1, 0, and 1. Okay, so just like we did yesterday. So R equals 4 plus 4 times a negative 1 is going to give us 0. Okay, now we think to ourselves, where is sine equal to a negative 1? Just like we did yesterday. So where does that occur? At 3 pi over 2. And let's go with degrees just to practice. So negative or positive 270 degrees. Now let's think about this for a second. Why did we get 0, 270 degrees? Because isn't that where it's going to touch? At the pole? Right? So we kind of already knew that point. All right? That was just finding it formally. r equals 4 plus 4 times 0, we're going to get 4. So we plug in 0. Okay, where is sine 0? At 0 and pi, so 0 degrees and 180 degrees. Okay, and finally plugging in 1, I get 8 here. And where is sine equal to 1? At 90 degrees. So 8, 90 degrees. So we have our 4 points. We know where it goes through the pole. We're ready to graph. Okay? So 0 degrees, 90 degrees, 180, 270. Okay, and remember, we're graphing, on that polar coordinate, or polar graph. We just have to kind of imagine what's going on there. Okay, so I'm going to plot my points. I have 0, 270 degrees, 4, 180 degrees, 4, 0 degrees, and 8, 90 degrees. Okay? You ready for this one? Just watch. Looks like a heart. You find the 2 points of symmetry, the one closest to it, that's where you're going to have, your heart shape forming, okay? And then this will be like the tip of the heart. So this is really going to be upside down heart. I'm just going to turn it so it's easier to draw. So, there you go. There's your graph. Pretty. You love it? Exactly. Yes. With a heart. It's okay. You can call it a heart. It's all right. It's a cardioid.
So does it always go through the middle?
Yes, it's always going to touch at the pole. Okay. Everybody good? Okay. Moving on. That's the only example we're going to do of a cardioid. Are you okay with that? Okay. It's like the same as yesterday, right? Okay. Now we're going to move on and talk about the next one. So the last type of polar graph is a lemniscate. These graphs look like figure eights. Okay. The equation for a lemniscate looks like this. R squared equals A cosine n theta, or R squared equals A sine of n theta. Okay, now you're going to have to go back a couple days to a rose curve. Doesn't this look just like the rose curve equation? Except what? It's squared. It's R squared. So that's how you know this is a lemniscate compared to a rose curve. Okay, see the difference? So there's really like, pairs of equations that kind of look similar. So you just got to keep them straight. And now there are rules. So like there were rules with rose curves, there are similar rules with lemniscates. Okay, so here we go. The square root of the absolute value of A is now the petal length. Remember with a rose curve, the petal length was equal to the square root of, the absolute value of A, right? So now you got to take the square root, but that's kind of easy to remember because it goes with the squared R. Okay, so that's how you can keep those two together. All right. N still dictates the number of petals, but now there are different rules. Okay, so let's do this. If N is even, then you have n petals. If n is odd, then you have 2n petals. What do you notice about these rules compared to the rose curve? They're flipped, right? Now let's think about why, because this is easy to remember. You can keep this straight if you remember this. These are figure eights, right? Well, imagine a figure eight looks like, you know, that, right? Every figure eight forms how many petals? 2. So don't we always have to have an even number of petals then? So that's how you can keep this rule straight, right? If it's even, then you're good to go. If it's odd, then you have to make it an even number of petals. Okay, so that's how I remember that rule. Okay? And then, again, the spacing between the petals you still take 360 degrees and divide it by the number of petals. So that's the same rule. Okay, then there's one more thing we have to figure out, and that's the starting point. Remember that? How you figure out the start? Okay, so the starting point, you have to follow these rules. So if A is positive, then you're going to take either cosine of n theta and set it equal to 1, or sine of n theta and set it equal to 1. If A is negative, then you're going to take either cosine, of n theta and set it equal to negative 1, or sine of n theta and set it equal to negative 1. So this rule is kind of easy to remember, right? Because if A is positive, it gets set equal to 1, a positive 1. And if A is negative, then it gets set equal to a negative 1. It has nothing to do whether it's even or odd anymore, okay? So in my opinion, these rules are much more common sense, right? They make sense. You can figure them out if you forget them, all right? Where the rose curve, you kind of have to memorize more, okay? Can we do some examples? Are you ready to see some? Okay. Can I move this page? Okay. Okay. This is going to be example 2. So r squared equals the sine of 2 theta. Okay, so we have to gather all that information like we did before. We have to find the petal length, the number of petals, the spacing, and the start. Okay, so how do you find the petal length? The square root of the absolute value of 1. Right? Because A in this case is just 1. So make yourself a note there. That's where that came from. A equals 1. So the length of the petal is 1. Okay? Now we have to decide on the number of petals. So n equals 2. And it's even. So how many petals do we have? 2. For the spacing, you're just going to take 360 degrees, and you're going to divide it by the number of petals. So each petal should be spaced at 180 degrees. And then finally, we have to find the start. So because A was positive, we set it equal to a positive 1. So we're going to have sine of 2 theta equal to 1. Now remember, this is something that I often forget, and I'll do this part wrong sometimes. I try to set it sometimes equal to a sine of n theta. Now in this case, a is 1, so you can't really tell the difference. But if this were like a 2 or something out front, that would be wrong. Okay, so just be careful that you're only setting it equal to sine of n theta, okay, or cosine of n theta. So again, this is a case where we have 2 theta, we have to replace it with y. So we replace it. Okay, so where is sine 1? Come on, this is an easy one. Where is sine 1? Pi over 2 or 90 degrees. We'll keep going with degrees. Okay, now that's equal to y. So we're going to set it back equal to 2 theta. Divide by 2. And theta equals 45 degrees. So we start at 45 degrees. Our first petal should be at 45 degrees. Tiffany. I mean, a little bit of it, so I know that you figured it out, but I don't care. I mean, this is a lot of work, you know, kind of talking it through, but a little bit, okay? All right. You ready for the graph? So 0 degrees, 90, 180, 270. Okay, so imagine those circles, you know, going around. I'll just draw them in here. Okay, here's our concentric circles forming that polar graph. Imagine that going on. Those are great circles, aren't they? Ish. Okay, so we start at 45 degrees. So imagine where that 45 degree mark is. Right? And then we're all 180 degrees around until we get to the next one. Right? So this is going to be at 225. Okay, now we have a petal length of 1. So I'm going to put a point here and a point here. And then you make your figure 8. So it looks like this. And you can just put a 1 there. If you want to label those 2 points, you can, like 1 45 degrees or, you know, 1 225 degrees. You can, but once we get a lot more petals on here, that's kind of aggressive labeling. So I would just say label the length and I'll be happy, okay? Just of 1, you don't have to label them all. Okay, you want to try one on your own? Okay. This is going to be our last example. So r squared equals 4 cosine of 3 theta. Find all your information first, and then graph. It'll always be r squared. Is that what you're asking?
So will A always be a perfect square?
Yeah. For our purposes. Okay. So let's kind of go through this one. For the petal length, did you get 2? Taking the absolute value of this 4 and then taking the square root of it. So for this one, n was 3. You can't have an odd number of petals, so you have to multiply it by 2, giving you the 6. Spacing is 360 divided by 6, giving you 60 degrees. Each petal is spaced out. The start was 0 degrees. Did you get that? Yes? So remember how before when we were defining our domain, we would always choose 0 over 360? It's really the same reason. Okay. All right, so now we have a space or a length of 2, right? And then every 60 degrees. So here, notice I labeled all of my angles. You need to do that, okay? Don't just draw in these figure eights. Label your angles. That's fully labeled. Okay, and notice I have one length of the petal labeled. So I am happy with this labeling. This is all I need to see for these. Okay, but you do have to show me each of those degrees. Yes?
Wait, so do we just do the first 2 quadrants because it's, we know it's the opposite angle?
No, you got to label all of them. Okay. Any questions? How many people got this one right? Yeah, pretty easy, right? You just got to keep the rules straight and you should be good. Yeah?
So for lima cards, you have to label all the things.
Yeah. Mm-hmm.